Today we are going to take what we learned last week about the observations of acid and base behavior and take it one step further to calculate or quantify their acidity and basicity using pH and pOH. And every acid-base solution that we're going to be looking at has to be in some sort of water solution. In our lab last week, you noticed they were all in test tubes with water base. And the reason for this is because when water interacts with these solutions, water itself actually will separate into OH and H through the process we call water ionization. And if we have pure water, then we'll have equal amounts, OH and H. If in the solution there's more OH, then it will be more basic, and if there's more H, then it will be more acidic. And that's kind of the idea behind this. When we have this ratio by which they ionize, we call it the equilibrium constant. Again, like I said, in pure water, they should be equal to one another. But if it's more basic, there will be more OH, and if it's acidic, there will be more H. So our ionization of the water, like I said, is the natural separation of water molecules. And so in order to find pH, it has to be in water. You have to have some sort of solution. And as we know with solutions, we are going to be working with concentration measured in molarity, moles per liter. We won't be doing any molarity calculations, but just remember when you see brackets, that means the concentration. We're going to be using brackets again. And so when these separate, then we will have H and OH produced. And just a little note here, because this is happening in water, our H will kind of hook up to another water, and used interchangeably with H is the hydronium ion. So if you see anything referring to H3O, that is the same as H+. So you can kind of use those interchangeably in this reaction. And you can see right here visually we have the water ionization. We have water, hydroxide, and hydrogen. And again, this hydrogen with water will make hydronium, and then we have hydroxide. And in pure water, let's make a note of this since I said it twice. In pure water, the concentration, there's my brackets, of the hydroxide separation is going to be equal to the concentration of the hydronium. Or again, I can just write H. Those are used interchangeably. But that is a helpful little note there of what pH is actually measuring. It's the amount of this stuff that has separated in the water. And if we kind of favor it towards the OH, then it's basic. And if we favor it towards the H3O, then it's acidic. Another term that we can use when discussing acidity and basicity is amphoteric. And water is amphoteric because it has both H and OH present. It can kind of act like an acid or a base. So an amphoteric substance is a substance that can exist as both acid and base. Water is one of those most obvious, or most common, I should say, of the amphoteric substances. So a substance that can exist as an acid sometimes and a base other times. And this is based on that Bronsted-Lowry definition. You know, acids are acceptors of hydrogen, acids are donors, they have to have the H, of hydrogen, and bases are acceptors of the hydrogen in a reaction. So any substance that can be both is amphoteric, and water is. water is amphoteric. Just depends on my levels of OH and H as well. Okay. Next, we have this KW, which I talked about earlier, this equilibrium constant, or the ratio between H and OH. And this is where we get our basis for making these calculations. So our KW, or the equilibrium constant, is a ratio, or constant ratio, between my separated waters. Constant ratio. Between H and OH. And for water, when we hit kind of an equilibrium point, or it kind of stops changing between the two, that equilibrium constant, or the relationship between hydroxide and hydrogen, their amounts, if you were to multiply them together, you would get this number. And you don't really need to know much about how equilibrium constant works, just that it exists, so you can understand kind of where this pH relationship comes from. So our equilibrium constant comes to be 1 times 10 to the negative 14th power. And so when we find this relationship, depending on, if you have more OH, then you have less H, and vice versa, that together we rewrite this as pH and pOH equals 14. And if you kind of look at this exponent, that is our relationship between concentration and pH that we will discuss here in a minute. But we have this really important relationship between pH and pOH, that it will always equal 14 when you add them together. So their sum will be 14 no matter what for a given solution. And that's really helpful for us. If we know the pOH, we can find the pH by subtracting the given value from 14, and vice versa. Whenever you see the P, like pH, pOH, that just is a mathematical symbol for negative log. And in your calculator, you would just click the negative sign and then the log, and then type in the concentration of whatever you're P'ing. pH would be representing the P of the hydrogen concentration. So you would do negative log of however much hydrogen there is, and for pOH, you would do the negative log of your hydroxide concentration. So whatever's after the P, that's what you would type in after your negative log. So just a couple of logarithmic properties before we do some examples with this math. So grab a calculator if you don't have one. Logarithms relate tenfold change. Log base 10. And since we're working with concentration, we're just going to keep it in terms of that. So our logarithm relates tenfold change in concentration. And so if I have the concentration itself, then I'm going to have 10 to the negative pH. That will give me the kind of to go backwards to what we just did in the negative log box. And same with our OH. 10 to the negative pOH will then reverse the log process and give us the concentration. So these two boxes also give us some important mathematical information. It's kind of like subtraction and addition. They're opposites of each other, or multiplication and division. So this would be log and undo the log, if you will. So let's do some math problems and see if we can figure these out by applying. So calculate the pH of a solution with hydronium equal to 6.59. So in our boxes, we said pH equals the negative log of our H. And again, remember H and H3O are used interchangeably. So you'll just type in your calculator negative log of that number it just gave us, 10 to the negative 10. And then make sure you put that negative sign in there, otherwise you're going to get a negative number. And we get 9.2. Now before we just move on, I want you to notice this negative here. Negative 10 is our kind of point of reference, I like to call it, so that we can say our pH should be around 10. Since we know that the concentration is 1 time, the pH, 10 to the negative pH power. And although this is not 10, we have our pH right there, which will help us kind of figure out that base 10 exponent should be close to your pH. What is the solution's pOH? Well, we have pH. We know that the relationship between the two equals 14. So if we just subtract our pH from 14, then we will have our pOH. So 14 minus 9.2 equals 4.8. There's our pOH. There's our pH. Find the concentration of OH. So if we have pOH, then we can work backwards to find our concentration of OH, knowing that it's 10 to the negative pOH. So put that in your calculator, and we get 1.6 times 10 to the negative fifth concentration. Remember, that's measured in molarity. And the last one, is this a basic, acidic, or neutral solution? We know from last week that high pH is basic. This is a basic solution, and that's because we have more of our OH than we do of our H3O. If you look at these concentration values, the OH amount is much higher, so it offsets to be more basic in nature.